All right, so now we're going to talk about systems of higher order differential equations. Okay, so let's look at the general form of this. So we're going to have components of a vector. Y1 is equal to some component of a vector field. And y2 prime is f2 all the way down to yn prime is fn t y1 to yn. And so this is a system of first order equations. And of course, what you can do is you can write this compactly in vector notation. Okay, so there's a condensed sort of vector notation. But this where I have, say, a big Y, which is a vector of these components y1 to yn. And it's a map from R to Rn, so it's a function of time, if you will. Okay, and then you have the vector field f, which is a component, consists of these components f1 to fn. Right, and this is a map from, let's see, so it depends on time, and it depends on y1 to yn, so I think of it as a map from r cross r to the nth power to r to the n. Okay. All right, and with that notation, you can rewrite the system of first order equations as just this y prime is equal to f of t and y, right? And then you can set up an initial condition for this, that y at time t0 is, let's say, y0. Okay, so the basic idea, if you will, is that what we want to do is to rewrite a system. Well, you would rewrite it's like higher order differential equations into a system of first order equations. So I want to rewrite sort of higher order differential equations into sort of a system of first order equations. Okay. And the reason why I want to do this is because when a higher order differential equation is written in this equivalent system of first order form, which is sort of this thing, then you can apply many of these one-step methods which we've developed, as well as multi-step methods which we've talked about before for solving scale value differential equations. But everywhere you see a y, it's like you think of now this y as being a vector, and every time you see an f, you think of it again as being vector valued. Okay, and so many of those methods will sort of extend in a very, very natural way to systems of first order equations. So that's the main motivation, is that by rewriting, again, a higher order differential equation into a system of first order equations, we can leverage, it's like the methods we've developed, it's like which were originally developed for scalar differential equations. Okay, so that's the basic idea behind this. So what do I mean by rewriting a higher order differential equation into a system of first order equations? So let's see what's happening here. Okay, so I'm going to just erase this. Okay, so let's consider sort of a higher order differential equation. So what is meant by higher order differential equation is something which involves, as the name implies, higher order derivatives. It's like of the function y, which is the unknown. So let's just say the nth derivative, so y superscript n with the parentheses denotes the nth derivative of y with respect to time is equal to some function f of t, y, y prime, all the way up to, say, the nth minus first derivative of y. Okay. So we're going to consider this to be the general form of this higher order differential equation. So in particular, you have to solve for this nth derivative, okay, in terms of t and y and its derivatives up to n minus 1. Okay, and then what you're going to do basically is that you're going to rewrite this as a system of first order equations by doing the following substitution. Let's say x1 is equal to y, okay, and x2 is equal to y prime, all the way up to xn is equal to the nth minus first derivative of y. Okay, so so this kind of substitution is the net effect of writing this right-hand side as t x1 to xn. Okay, so with this substitution, this becomes f of t x1 to xn. Okay, and of course the left-hand side becomes xn prime. Okay, so that's one of the equations. Xn prime is equal to f of t x1 to xn. And then we want to write the other equations. Okay, so the other relationships, so I still want sort of x1 prime all the way up to xn minus 1 prime. Okay, so let's see what happens. So x1 prime is equal to y prime. Y prime is equal to x2. Okay, so x1 prime is equal to x2. And you can see that sort of the same kind of pattern, it's like persists. So n minus 1 prime is equal to xn. Okay, all right. So so what's going to happen then is that with this substitution, right, I can rewrite. So I can rewrite this yn equals to f of t y prime to yn minus 1, right, as the system of first order equations which have the form x1 prime is equal to x2 all the way up to xn minus 1 prime is equal to xn, and xn prime is equal to f of t x1 to xn. Okay, all right, so that gives me the system. And all right, so that's just for a single higher order ODE, and then the same approach, if you will, can be applied if you had systems of higher order ODEs, right? And you just had to do this, it's like one by one. Okay, so right, so we just talked about a sort of a scale-valued higher order ODE. It's like with this, but I mean it extends sort of in a fairly natural fashion to systems of higher order ODEs, if you will. Okay, all right. So perhaps let's look at an example of this, just so that it's clear what is going on. In fact, let's look at a system that's like of higher ODEs. It's like just so that we know exactly what we're doing here. Okay. So I'm going to look at a system of two second order ODEs. Okay, so this is a system of two second order ODEs. Okay, So let's say x double prime squared, right, plus t e to the y plus y prime is equal to x prime minus x. Okay, and y prime, y double prime minus cosine xy plus sine txy is equal to x. Okay, all right, so the first order of business again is to do these, or sort of set up the substitutions. Okay, so let's say x1 is equal to x, okay, x2 is equal to x prime, x3 is equal to y, and x4 is equal to y prime. Okay, so I've put both the x and y as well as derivatives that's like into this vector of x components. All right, so I know that x1 prime is equal to x2, right? And then x2 prime, which is x double prime, is equal to the other stuff. So I have to rewrite x2 double prime. It's like in terms of this thing. So x2 double prime is equal to x prime minus x minus t e to the y minus y prime to the 1/2 power. Okay. So I'm just solving here for x double prime. It's like in this equation. Okay, and then I can now transcribe it. X prime is x2. So this is x2 minus x is x1 minus t e to the y. Y is x3 minus y prime, which is x4, again to the 1/2 power. Okay. Okay, that looks right. Okay, and then x3 prime is y prime, which is x4, and then x4 prime, which is y double prime, okay, is equal to 1 over y prime, okay, x plus cosine xy minus sine txy, which is, okay, 1 over, y prime is 1 over x4, okay, so 1 over x4 multiplied into x, which is x1 plus cosine x and y, which is x1, x3, x1, x3, minus sine t xy t x1, x3. Okay, so all right. So hopefully you get the idea, right? We didn't write down the most general form. It's like of the systems of higher order differential equations, but this example should illustrate the basic idea behind this. So you do what you would have done. It's like if there was just a single, it's like higher order differential equation, which is that you write down x1 to x sort of n, x1 to xn, it's like which involves x to the nth minus first derivative of x. It's like, and then you sort of keep doing this now with the y's. It's like with the new terms, and then with that you rewrite the two equations. It's like in terms of these substitutions, right? Where you have to solve for the highest derivative. It's like in each of these equations separately, right? Which is what I've done here. Okay, so that hopefully will give you an idea of what's involved. Okay, so that's for systems of high order ODEs, and then it's like the next thing we'll talk about is many of the methods it's like which we're going to study. It's like are simplified if the differential equation is not explicitly dependent on time, which is to say that the vector field doesn't depend on time, it just depends on x1 to xn. So we'll talk a little bit about that in a little bit. So let's just stop for now.